Hello, Algebra 2 class. Our topic for this video is going to be our last topic in this chapter. It is transformations of exponential and logarithmic functions. Our objectives, as you can see, we're going to be writing functions if I tell you what the transformations are, and we're also going to be going the other direction. If I give you a new function, I want you to be able to tell me, well, what transformations happened in order for us to get there. Just a super quick review because I think some of us need it. Some terminology we'll be using in this is going to be the parent function. So a parent function is just the simplest function in a family of functions. Generally, the parent function will be the starting place for each of these problems, though. So for example, if we think back to some of the other functions we've talked about before, the ones we're talking about in this chapter, we were working with quadratics and working with polynomials, and we'll be looking at, in this case, cubics specifically. The parent function for a quadratic, right, the simplest quadratic function, is just f of x equals x squared. And generally, if we were doing a transformations problem, right, we were trying to figure out, well, what happens when I shift this up or down or left or right or stretch it out, this would be our starting point. Right, for cubics, our starting point, our simplest function in that family, which is f of x equals x cubed. There's a little more room for debate when you're working with exponentials and logs as far as what is the simplest function in that family, but the ones that we'll be using in our class are going to be for exponentials, f of x is equal to 2 to the x. Nice, this is 2 raised to the an unknown power. And also, for logarithmics, f of x is equal to log base 2 of x. Right? So in both cases, we'll be using that base of 2, just an exponential in one case and a log in the other. I also want to do a super quick review on what these things actually look like on a graph. So just some super fast sketches here. If we have a vertical stretch or compression, let's look at, for example, a quadratic function, right? Let's say we have one quadratic that looks kind of like this. This is our original f of x. And if we want to vertically stretch that out, that means that all of our y values are going to get farther away from the x-axis. All of our y values are going to get bigger. So in this case, well, these are right on top of the x-axis, so they stay there. But all these other ones are going to get stretched out. This will all get taller. And over here, the same thing will happen. They will all get taller. Now, my drawing should be a little bit better, but we're sketching right now. So this would be our new g of x after a vertical stretch in this case. Now, a compression would go the exact opposite direction. All of our y values would just get shorter. For a vertical translation, right, a translation just means a shift. So this is just our entire graph going up or down. That's the vertical piece. So again, if we start out with some f of x, let's look at this cool function here. And I want to vertically shift this, let's say up a certain amount. I would just take that exact same graph. Everything stays the same except now it's up here instead. Okay, so this is a vertical translation up by maybe, well, my sketch isn't perfect, but probably 1, 2, about 4.5 or 5 units. A horizontal translation is just the other piece of that. This is a shift still, but it's to the left or to the right. So if we just draw any old graph on here, right, let's draw this graph like this. If I take something like this, and I want to do a horizontal translation to the left, let's say, that would just take our entire graph. Nothing changes except the entire thing gets shifted over to the left. And there's our new g of x after it's been horizontally translated.